Welcome everyone. Thank you for your attendance to this online training seminar. It is 10 a.m. AA Eastern Australian time, and we will begin. I would firstly like to introduce myself and my colleague. My name is Michael Davies, and I'm a metallurgical engineer who graduated with a bachelor's degree from the University of New South Wales. I have over 35 years experience in the iron and steel industry in Australia, including roles with BHP, One Steel and Molycop. I am assisting the Australia and New Zealand chapter of AIST this year. Also online today, we have Dr. Shabnam Saba, who is a postdoctoral research engineer at Swinburne University of Technology. Saba is currently involved in the HILT CRC funded projects focused on the prevention of sticking in hydrogen fluidized bed DRI production and de-risking of electric smelting furnaces for Australian ores. Saba is also the Vice Chair for the Australia and New Zealand chapter of AIST. Before we start the webinar, I wanted to take a few minutes to give an overview of the Association for Iron and Steel Technology, AIST. To start, AIST is an apolitical organisation. Our mission and vision are both technical in nature, which makes us unique to most trade organisations in the world. I'm excited to announce that for the first time in the organisation's 154-year history, we have over 19,000 professional and student members. If you are not already a member, we would love to have you join. Next slide, please, Johann. Although AIST is headquartered in the USA, our mission is without national borders. So we promote membership wherever there is a strong value proposition to fulfill our mission and vision. We now have 22 member chapters on 6 continents. Each chapter conducts their own activities in their region. With this extensive network, AIST is positioned to interact with the global steel community and disseminate information about the latest technology advancements for steel wherever they may be evolving. Next slide, please. While our member chapters engage members within a specific geographic region, our technology committees engage members who are focused on a specific process or technology. AIST has 29 technology committees organised within 9 divisions. These committees currently include 4,000 participants from 45 countries, which makes it the world's largest and most diverse network for steel manufacturing expertise. I encourage you to consider joining an AIST technology committee. They are free to all AIST members. Next slide. Thanks, Johann. There may never have been a better time to be involved with AIST. Our membership grew 2% from record numbers in 2025, as I mentioned, to over 19,000 combined professional and student members. It's the first time in the history of the organisation we've been over 19,000 members. Professional membership is currently over 15,000, breaking the record we hit just last year. If you are not already an AIST member, our benefits include access to our technology committees and member chapters, as I just spoke about, also the monthly Iron and Steel Technology magazine, and discounts on conferences, events, and publications. There are special programs available for young professionals under the age of 30 and students. Thanks to the AIST Foundation, young professionals get their first year of AIST membership free. Next slide, please, Johann. AIST prides itself on providing the tools that steelmakers need to succeed, no matter what level they are at in their career or where they are in the steelmaking process. We have programs for professionals, students, academia, trade schools, and young professionals. Next slide, please, Johann. Before we start the webinar, I just wanted to take a few minutes to talk about some of the events that are happening in Australia. The 7th Annual AIST Australia and New Zealand Steel Symposium will be held at CSIRO Laboratories in Clayton, Victoria on the 10th and 11th of February, which is next week. The symposium includes 2 days of world-class presentations on the iron and steel industry, followed by site visits to view the facilities at CSIRO and Monash University, the Calix Zesty pilot plant, and the Infrabuild steel mill in Laverton. Next slide, please, Johann. The Australian and New Zealand chapter of AIST and HILT CRC will also be conducting a training course titled An Introduction to DRI Processes on the 9th and 10th of March in Perth, Western Australia. This course will be presented by Professor Jeff Brooks and Johann Rinnhofer, who is also presenting today. Professor Brooks has published over 300 papers on the fundamental aspects of iron and steel making and has worked closely with steel companies in Europe, Asia, and North America. Professor Brooks is also the chair of the Australia and New Zealand chapter for AIST. The AIST website, www.aist.org, has a full calendar at the top with a schedule of all the upcoming events. I would encourage everyone to please review these events and attend where possible. Next slide, please, Johann. Before we start the webinar, there are 2 AIST governance areas to cover. AIST's antitrust guidelines emphasise the law that prohibits agreements between 2 or more individuals or businesses to regulate prices or quantities of goods and services, to allocate customers or territories, to limit a competitor's operations or otherwise unreasonably restrain business activity. Everyone who participates in any AIST activity must follow these guidelines. Next slide, please. AIST's anti-harassment policy emphasises the importance to provide a harassment-free environment regardless of age, race, religion, disability, or gender. Please, Johann. The topic of the training webinar today is reheating furnaces for the steel industry. We're very fortunate to have Dr. Johann Rinnhofer, who is the CEO of thyssenkrupp nucera Australia, based in Perth. Dr. Rinnhofer has 30 years of experience as a CEO in the plant engineering businesses for the mining and metallurgical industry, including fuel and induction heated industrial furnaces, hydrogen, and power plant technologies. Johann serves as an honorary professor at the University of Leoben in Austria, where he lectures industrial furnace technology. For everybody's information, this online training webinar will be recorded and it will be available on the AIST website. Johann will be answering questions at the end of the presentation. Participants will be on mute during the presentation. Please submit your answers to the Q&A feature on Zoom rather than the chat function, so we can track the questions and ensure that all questions are addressed. The presentation is expected to end at approximately 11:45, which will provide 15 minutes for questions at the end. We may also have a brief 5-minute intermission during the webinar after the first hour. Thank you very much for your attending, and I will hand you over to Johann.
Yeah, thank you very much, Michael, for the kind introduction. It's a bright and early start here in Perth, 7 o'clock in the morning. Quite unusual to be in the office at that time. Today's webinar is about reheating furnaces, and we would probably like to start with a little video at the beginning. What we will cover in the webinar generally will be fuel-fired furnaces, heating strategies, energy consumption, and also the fundamentals of heating a body, heat transfer, and the use of Biot and Fourier number. calculate heating times. And in the second part of the session, we will deal with electrification of heating processes, including resistance heating and induction heating. So probably let's go into this little video.
Steel is highly resistant to shaping when it's cold, and for that reason, it's generally rolled whilst it's hot. To make sure the steel is at the correct temperature for rolling, it's fed into a furnace. Here it travels through several temperature control zones until it's at the correct temperature and ready for rolling. Whatever the product, the principles of hot rolling are the same.
It was a very short video just showing the walking beam furnace in a rolling mill. But why are we doing that? What is steel? Steel is, as you can see here on the iron carbon diagram, iron carbon alloy with a carbon content of less than 2%. It has different melting temperatures, so it can be 1500 degrees. It can also be 1150 degrees only when you have a carbon content of 4%. So it's a very interesting material. We have more than 3,500 types of steel for that reason, because we have so many options to alloy steel with carbon and also other alloys like chromium, nickel, and other metals, and also heat treats them in different modes, so to say. A very interesting feature is the different crystal shapes which we can have. This is the austenite at high temperatures and the ferrite at low temperatures, and all sort of combinations in the end. What we will also need later is a special feature of steel, which is the magnetic properties of the steel. So below the Curie temperature, which is around 770 degrees C, steel is ferromagnetic and it is non-magnetic beyond that temperature. So that is very important for induction heating. So this is why this is important. Typical heating temperatures are for reheating in the area of 1200 degrees, because steel is malleable at this high temperature in the austenite area, basically. This is because we have a face-centered cubic crystal structure which offers slip systems. So you cannot shape and form steel in a cold condition like you can at these high temperatures, as we all know from the forges. I'm actually a member of the Blacksmith Association of Western Australia. This is why I show the picture here on the right upper corner. What is very significant is the magic line around 900 degrees. So this is this red line where you sort of come into the austenite area, and you can change the shape of the crystal, as we said in the beginning already, from body-centered into face-centered. This is why we always have to pass this magic line, the austenite line, for heat treating, for austenitizing and hardening, for example. And tempering can be at much lower temperatures because we don't necessarily change the crystal shape again. And during a rolling or forming or forging process, the grains of the austenite grains are constantly broken down and also recrystallized again. So this is why we get a very specific crystal structure in a forged or rolled product. And we have all sort of technologies like thermomechanical rolling and other things. We cannot go into too much detail here now. So apart from the temperature, we also have to set the starting austenite grain size before rolling, because that also will influence the final structure and final quality of the product in the end. So there we have two significant variables. This is the time, heating time, and also the heating temperature. Whereas it is very important not to heat at too high temperatures, because you will get very, very coarse grains, which we don't want. So we want a very uniform and sort of small grain-sized austenite structure before rolling. Another topic is the dissolution of precipitates in the steel. You see this little diagram here. So at high temperatures, some metals are dissoluted in the steel structure, and also the grain diameter will grow when you heat for a long time. And another very well-known issue is the surface oxidation and also decarburization of the steel surface, which happens at very high temperatures of more than 800 degrees excessively. So you have to watch the furnace atmosphere, especially also the oxygen content in the furnace atmosphere, which can be caused by false air, which can be caused by the combustion system when you have too much air in the burner system. Let's look at the energy content of steel. Energy content means this is the energy which is incorporated in the steel itself, so to say, no matter how it is heated. You know, it's just this is special inner energy of the steel. This is around 220 kilowatt hours per ton of steel in the temperature range of 1200 degrees. It is around 400 when you have a melted steel in an electric arc furnace or in a converter or somewhere else. And this is the overheated melt, no? Because it's not good enough to melt steel. You also have to overheat it with a certain temperature to make a production process possible in the end, because it will cool down. And for austenitizing and also tempering, obviously we have much lower energy contents. It's actually a very interesting chart, because you can also see the different melting points of steel and iron carbon alloys. So we start here at the eudectic, at the lowest temperature, so to say, 1150 degrees approximately, and it can be as high as 1530 degrees. So when we look at the major energy consumers in an electric arc furnace based rolling mill, you see the electric arc furnace. You know, we have this 385 to 400 kilowatt hours per ton incorporated energy in the steel, which in the end will require us to spend 650 kilowatt hours per ton approximately, because we are operating a real process with energy losses and all the other things which come with a process which happens in real conditions. The same is in the reheating furnace. So we have this 220 degrees, which we will end up with 330 approximately, because we have losses. And the rolling stands, they also have an electric energy consumption. And you can see that the electricity in this whole process is approximately, say, 40 to 55% of the total energy demand of these three aggregates, and the fuel is around 45 to 60. This is depending on how you run the electric arc furnace in the end, because you have different options. Either you use very, very low electric energy in the electric arc furnace and a high fuel rate, or the opposite. So you can also run it at very high electricity consumption with low fuel consumption, but we will never completely eliminate the fuel consumption in the electric arc furnace. So the name electric arc furnace is a bit misleading in this sense, but this is how it is. So in the end, the energy consumption of a reheating furnace can also be much higher than this 1.2 gigajoule per ton or 330 kilowatt hours per ton. It's depending on the type of furnace. So we are focusing here at the rolling mill furnaces, continuously operated furnaces There are different other options. We have rotary hearth furnaces, we have batch type furnaces, and all sort of things. In the end, we will have CO2 emissions of 70 to 100 kilos per ton of steel by burning fuels in the end, when you use natural gas. This doesn't sound a lot because in a blast furnace operated mill, we have around 2 tons of CO2 for 1 ton of steel. On the other hand, a reheating furnace is very easy to measure. So when you look at it, you can easily determine scope 1 and scope 2 emissions. So it's sort of easy to identify what's happening there with energy and also emissions. This is why we should look at it. It is certainly an important furnace. And in the end, as we said in the beginning, we look at alternative fuels and electrifying this heating process potentially. Walking beam furnaces looks approximately like that. We come in with the cold steel here on the left end and exit hot on the right side here. You see a discharging machine here on the right side, and in the furnace we have a steam cooled system of tubes, so like a stock carrier, so to say. And this furnace is heated from top and also from the bottom. It has usually 3 significant sounds. The hot sound, we have the soaking sound, which is basically the task of this sound is to equalize the temperature in the stock, so from the surface to the core. The heating sound, so in this, we operate here at very high temperature, so there's not a lot of heat transferred in that area, but it's an equalizing sound, so to say. A lot of heat we are transferring in the heating sound, which is in the middle here. We are heating up the steel, you know, we have still a lower, relatively low steel temperature, so it is a very, very good condition to transfer a lot of heat. This is a high temperature difference. We have large burners on the top and also on the bottom of the furnace. And this is followed by a convection sound, which is sort of separated here with this little nose on the top of the furnace. So we use the hot gases which are going to the left side here through the furnace into the flue gas duct here. And we try to get as much as possible energy from the fuel gases into the steel in that area. We have no burners here at all because it doesn't make sense to have any heating here, because all the heat will go directly into the flue, and this is what we don't need. So we would increase the temperature of the flue gas, which is not a good idea in the end. The whole system is moved with this system here, which you can see in the lower end of this picture here. So this is a walking beam mechanism which is basically moving the stock forward into the right direction. This is a front view on the left side, so that can be, say, 12 meters, that can be 15 meters wide. You see here the stock on the carrier system. You see the side burners, you see the top burners, and also the system, the walking beam system down there. It's a fairly large furnace, so you see it's not small. Top view shows the heating, the carrier system again, and also some billets in the furnace. So we come in here with a side door, a small door, you know, because we don't want to open the furnace if possible, because we don't want to have air in the furnace. So we have a small door only from the side. This is very good for billets, avoiding any forced air coming into the furnace. We move through the furnace, and at a certain point here, we go offset with the carrier system, because we want to avoid cold spots on the lower end of the slab or the billet, because that will affect the rolling process. So we have a little offset here. So we give this spot here the option to heat up until the end of the heating process, and then we take the billet or the slab out with the discharge machine and go into the rolling mill from here. When we look into the heating curve or the temperature curve of these furnaces, they usually look like this. So we start the heating process cold with cold steel, or it can also be preheated, but usually cold. And then we have a furnace temperature, which is in the range of, say, 700 to 900 degrees usually in these furnaces. And you have a very high temperature difference. So high temperature differences are very good usually for heat transfer, because the transferred heat is a function of the temperature difference from the furnace temperature to the surface temperature of the slab. So we're talking about the surface temperature only, not the average temperature of the stock. The surface temperature is shown here as the slab top temperature. This is the blue line here. The slab bottom temperature is the orange line here, and the slab core temperature is the red line. So what we always have to look at is the temperature difference in the slab. This is shown here as the delta T. It should not be too high, because we can get all sorts of mechanical problems and in the slab, including cracks when this temperature difference is too high. So we have to watch the temperature difference in the slab. We have to watch the surface temperature of the slab, and in the end, we want to come out with a very equal temperature, say plus minus 20 degrees or so in the slab. That's usually good enough for rolling a slab of 200 mil thickness. So this is why we have the soaking zone on the end. What you also see here, as we said in the beginning, no burners in the convection zone. We see very heavy heating in the heating zone. We increase the temperature of the furnace in the heating zone. We even go with the temperature higher than the final slab temperature in order to increase the delta T in the furnace, from furnace to the surface temperature of the slab, in order to transfer as much heat as possible in that heating zone. On the other hand, we want to have a very short period of time in the heating zone. So the residence time in the heating zone should be very, very low if possible, because we get this high oxidation in the area of higher than 800 degrees Celsius. So it's a bit of a catch-22. On the one hand, we want to have a high temperature here in the furnace to enhance the heat transfer. On the other hand, we want to minimize the slab, the scaling, the oxidation. So it's a very fine line we go there, what to do basically. You know? So how do we design this process here in the end? That's the question. And then we say, okay, scale is not good. So we're in the range of, say, 1% scale from the steel weight for such a heating process. It can be 3%. For example, I saw 3% already in rotary hearth furnaces where you heat billets for a rolling mill, for a tube rolling mill, for example, because you have a very high surface to volume ratio of these small billets which you're heating. On the one hand, this is an economical loss because you're losing material. I mean, you are burning steel, basically oxidizing steel. That gives also a little bit of heat, no? But steel, iron is not a very good fuel in the end. So scaling is bad on the one hand. On the other hand, it's good because you're healing surface defects, no? On the steel, which is sort of exposing virgin steel again, which is a good feature of scaling. No? So it's not only bad, it's also good. So this is how it looks like. We are heating such a billet of 200 mil in a sort of time period of 180 minutes approximately. Yeah? So this is just an indication. How does these furnaces look like? This, you come in cold on the left side, you go through the furnace, you end up here hot, and exit the furnace here also through a little door on the side in order to prevent air ingress. You see the small burners here in the soaking zone because, as I said, not a lot of heat transfer, small burners. We have a lot of heat transfer in the heating zone, large burners. And you see here the insulated air system. This combustion air is usually heated to 400 to 600 degrees Celsius in order to save some natural gas. That's another view. So here you come in from this side, cold, come in here and come out hot here. Small burners in the soaking zone, large burners in the heating zone. This is how it looks inside the carrier system. And you see here also there is an offset of the carrier system. And here it's all insulated. It's a completely new furnace. You see the burners here on the top, radiation burners. You see the castings here on the top of the carrier system, which are carrying the slabs or the billets. This is a typical radiation burner here in the middle. You see, it's a completely different concept than a high velocity burner, which is a high speed burner, which is sort of generating some convection heat transfer. And here we have radiation heat transfer. So this is the basic concept of these two types of burners. This is how a furnace looks like inside. See the refractory system, which is usually a aluminum oxide, silicium oxide system, refractory, and all precast or cast parts here. You can also have bricks, obviously, but this is usually how it is done today. When you look at the energy flow of these systems, of the reheating system, usually we have this concept. So we have the metal coming in cold, we have the metal coming out hot, and then we have air coming in and fuel coming in on the left side. The air comes in at a preheated temperature because preheating of air is saving energy in the range of 15 to 25% and even more, depending on the temperature of the air. There are also different concepts of air preheating. So we have this recuperator as it is shown here. So we take the hot gases from the furnace, go through a recuperator and preheat the cold air, which is going to the burners in a warm state, say at 400 to 600 degrees approximately. There are also other options like recuperative burners. So you have the recuperator in the burner system. They are usually used for normalizing furnaces and also some sort of lower temperature furnace, a bit less than 1000 degrees approximately. And we also have the option to go to regenerative burners, which are dealing with very high temperatures. You can use them in the hot zones of a furnace. They have preheating temperatures of around 1000 degrees Celsius and even more. But you can use them only in the hot zone of the furnaces, obviously. And afterwards, you can go into a kind of, you can use this exhaust gas still to produce steam. Or you can do other things with it. There are other options of heat recovery. In the end, you will end up in a stack. The exhaust gas will go through the stack, and you have to control the draft of this stack by a damper, which is shown here on the right side. This is important because we want to control the furnace pressure. It has to be usually a slight, very, very slight overpressure in order not to blow out too much of the useful energy from the furnace doors and openings. And on the other hand, very important also, it should never be a negative pressure, because you would suck in force air and oxidize the steel, and also heat up air in the furnace, which is unnecessary, because air has a very, very high energy content. So 1 kilogram of air has approximately 1 kilojoule per kilogram and Kelvin. Steel has 0.6 approximately at 1000 degrees. So 1 kilo of air has a higher heat capacity than steel. So looking into more detail, so what we do, we look at the energy flow in the metal, here shown on the bottom, and also the energy flow of the gases. So we have the incoming gases, which is the fuel, and also the hot air with the sensible heat in the air that goes into the furnace, and out comes the flue gas. And there's a difference between these two energies. So we have the fuel and air coming in, and the flue gas going out of the furnace. And if we relate this to the energy coming in with the fuel, we have this heating efficiency. So the difference between the incoming energies and the outgoing energies, when you look at the gas only, they are sort of useful to these energies go into the metal and also the losses of the furnace in the end. So we can say the thermal efficiency or heating efficiency of this furnace you can describe by the difference of the gases coming in and coming out, the energy of those gases, and they are covering the metal and the losses, the heat of the metal and the losses in the end. So this is how you can calculate, and we don't do this in more detail here. You can calculate the thermal efficiency of this furnace. They are around for rolling mill furnaces, they are around 0.65, 0.7, 0.8 maximum, I would say, for a continuously operated furnace. So you always have some losses, and usually we will see that the flue gas loss is the highest loss. And here we are. So when we look at the slab at around 1200 degrees, this is the yellow arrow here, we find again our 220 kilowatt hours per ton here. This is the energy content of the slab. And we see all the losses, all the losses around. We see especially the off-gas or flue gas loss, which is very high. This is the red area here. This is why we use this high energy to preheat the air again. This is the typical Sankey diagram of a reheating furnace. So we see the impact of the air preheating. So you have approximately 10 cubic meters of air for 1 cubic meter natural gas. You have approximately 33 cubic meters of natural gas for 1 ton of steel. So that equates into 330 cubic meters of air, or 400 kilos of air for 1 ton of steel in the combustion process. So when we calculate the energy in the combustion air now at 450 degrees and also 1000 degrees, we will end up at 52 kilowatt hours, just sensible heat in the air, or at 1000 degrees, more than 100 kilowatt hours per ton of energy in sensible heat in the air. And when you compare this with the energy in the gas, which is 330 kilowatt hours per ton approximately, you see this is a lot. Yeah? So you really can save energy when you preheat the air, either by a recuperator or even regenerative burners, which are rather shown here in these orange numbers. Here we have another Sankey diagram of a 140 tons per hour walking beam furnace. So the inner dimensions are 18 meters long, 15 meters wide. Discharge temperature is 1175 degrees for square billets, 160 mil, 15 meters long. We don't go into too much detail, but you see again the same pattern. You have the hot air, the flue gases coming out, and the recuperator, which enable us to preheat the air. And here again, you see here in this furnace, you have hot air supplying approximately 18% of the energy back into the furnace again. So that's a lot, and this furnace is not even optimized, I would say. So it can be 20, 25, and even more. So what to do? So what are the variables and the parameters we can optimize? So we can obviously try to increase the stock inlet temperature. That will help. No? If we come in with 300 degrees, obviously we need less energy to heat it up in comparison to room temperature. We can try to reduce the flue gas temperature, because as we have seen, the flue gas is the highest loss of the furnace. So if possible, we want to have a low flue gas temperature. How can we achieve that? It's not so easy. So we have to improve the heat transfer in the furnace, or we can make the furnace longer, which we usually don't desire, because we want to minimize the footprint and also minimize the cost of the furnace. So yeah, you have to make decisions in the end. No? So there's no 100% one-fits-all solution. You can change the heating strategy. You can go higher with the temperature here in the heating zone, for example. What does it mean? You have higher temperatures in the stock, and so on and so on, scaling, all sort of things. You can reduce the whole processing time by improving the heat transfer. What does it all mean? It has to be really carefully looked at. There's no, as I said, no one-fits-all solution. It has to. So every furnace is different in the end. So, but in any case, you have to look at air preheating. You have to look at the flue gas volumes. So, for example, when you have natural gas and you want to use another fuel like hydrogen or something else, you might have, or oxygen instead of air, you might have completely different flue gas volumes, which are lower than natural gas flue gas volumes. They completely change the heat transfer and also the pressure in the furnace, for example. So you can look at the burner systems. You have to look at the scaling and decarborization topic, and in the end, how do you achieve all that with different zones in the furnace which you can control? That means you have to split the combustion system into different zones, and also control those zones in the end. Just showing an example, we earlier used to optimize furnaces, also not only building new ones, but also optimizing, as I said, heating strategies or the way how you operate a furnace. This shows a 100-ton slab furnace in Germany, actually, length 30 meters, wide 7 meters approximately, heating slabs of 245 mil thickness. And that furnace has a soaking zone like traditionally built as a ceramic soaking hearth, basically. That's the usual way how they built the furnace in earlier times. So we have the flue gas going out through the bottom here, which is actually a good solution. We don't want to go up here if possible, so we want to go down in order to drive the flue gas down over the slabs into the flue gas duct. We have a little convection zone here, and then a very large burners here on the bottom of the furnace in the heating zones here, and a lot of roof burners here. In the end, we have no option to actively heat the soaking hearth from the bottom here, because there is a ceramic hearth. There's no way to change anything there. So it's very it's not very good in the end for heating. And I will show you why. So what we did in the end, just to preempt it, so we took out this soaking hearth. So we dragged it down completely in a few weeks and rebuilt it with an actively heated soaking zone. That is shown here on the right side. So now we can have burners here. We can have actively heated area in the bottom of the furnace here. And obviously the upper part was left as it was originally. And so that gave us the option to completely change the heating strategy. Originally, the furnace looked like that. So we had, as I said, very large burners here in the lower furnace. That means the slab bottom temperature went up and went up. It was very high temperature, a lot of scaling there. In the end, very high temperature differences in the stock, all sort of things you don't want to have. And that was necessary in order to arrive here before we go into the soaking zone, at a very high temperature, because we have no option to heat from the bottom in the soaking zone here. That means we have to put all the energy which is needed into the slab in that area on the left side. So there was no option to heat in that area. So equalizing is shown here now. So we lose temperature again, and in the end, we have a certain temperature difference between bottom and top in the end of the heat, at the end of the heating process here, and we go into the rolling mill. So that is not ideal in terms of scaling. This is not ideal in terms of energy consumption, and so on and so on and so on. So what is the situation after? It looked like that. So we had changed the soaking hearth, as I said, into an actively heated lower zone. And now we can reduce the temperature of the slab surfaces, top and bottom, and sort of avoid scaling for that reason to a higher degree as before. We can actively heat the bottom of the furnace in the soaking zone. That means we are still increasing the temperature here, and we have a really good temperature difference, a very low temperature difference at the end, which is very beneficial for the rolling process and the quality of the end product. So that's in short the option we have now, because we rebuilt the furnace completely to a different heating strategy. And this is how the slabs looked like. So we are measuring the temperature here with this little box which is sitting on the slab here. You see a little bit of scale here. Actually, when you look at into a furnace, when you look at the scale, it usually with the pyrometer it shows a higher temperature than the slab, because it's brighter than the slab. When you come out with the slab onto the rolling onto the roller table, the scale will cool down and it will show a lower temperature actually. So you measure a lower temperature when you look at the scale. When you're outside the furnace and you measure a higher temperature, when you look into the furnace at the scale. And so you have to be careful what you measure when you look with a pyrometer. The end result is we have reduced energy consumption of the furnace. The modernized furnace is showing here the red columns. So we have an energy consumption reduced by 9% in comparison to the original situation, and also to the furnace number 2, which is sitting next to the furnace number 1, which is sitting next to it. So say 9% energy consumption, we have a reduction of the waste gas temperature of minus 124 degrees. Reduction of waste gas temperature means we reduce the energy loss, the sensible energy of the fuel, of the flue gas, so to say, which we lose. So that means the lower the temperature of the flue gas, the better it is. And this is why we have 9% energy consumption in the end. There were a lot of other features, including scaling and other quality issues, which were influenced very beneficial by rebuilding this furnace. But it shows, it's a very typical example what you can do when you really carefully look at the reheating process. This is how such a furnace can look like. This is just one option. Very hot. And hot again. You see the ducts here, all insulated air ducts. Very nice furnace. Another one is a walking beam furnace for slabs in Denmark, actually, Dansteel. You see here the exit of the furnace. Just a few data of this furnace. It has also 100 tons per hour. It has 200 to 400 mil thick slabs. So it's fairly thick slabs. No, it's a heavy plate mill. You have only 0.65% metal loss. That means scaling, which is a very, very good value. You wouldn't have that with billets, most likely, because here you have a very small surface to volume ratio with these slabs. As I said, you can have 3%, you can have also more than that when you look at rotary hearth furnaces and sort of small sized stock. Very interesting, you see here 31.4 cubic meters of natural gas. I estimated this with 10 kilowatt hours for 1 cubic meter of natural gas, lower heating value. So you arrive at 1.1, 1.2 gigajoule per ton, or again, our 330 approximately kilowatt hours per ton, again, related to the energy content of the steel, which is around 220 kilowatt hours per ton. How do you heat a 250 mil slab in comparison to a 400 mil slab? You see the difference is the heating time, obviously, but everything else is very much the same. So in the end, you end up with 1 minute per millimeter or 1.4 minutes per millimeter thickness of slab when you just look at it in average. No? So this 1 minute per millimeter is a typical heating time, specific heating time for, say, 200 mil slabs. Let's go into the fundamentals. What is the Biot number? So that describes the thermal thickness of a slab, for example. So what does that mean? So we have an external heat flow. This is the heat carried from the outside to the slab. This is the heat transfer coefficient times the furnace temperature, the infinite minus the surface temperature of the slab. And we have the inner temperature surface to the center at X is S. This is the thickness of the slab, so to say. When you have the slab sitting on an adiabatic hearth, that means this is a kind of insulated hearth. There's no energy carried over that line into the hearth, so to say. This is an idealistic view of this slab sitting on an insulated hearth, so to say, hearth. So we have external heat flow and internal heat flow in the system or in the slab. And when we say external is equal to internal, we are ending up with this equation here. So then what we do next, we put all the temperatures on one side, the right side, and all the other properties on the left side. So we end up with H, the heat transfer coefficient, divided by the heat conductivity times S, the thickness of the slab. And that is the Biot number. So that describes the thickness, the thermal thickness of the slab. So it can be thermal thin when Biot is less than 0.1. It can be thick when Biot is more than 0.1. So this 0.1 barrier is a little bit arbitrary, but this is how it is usually used in the literature and in practice as well. So we can say something is thin if you can neglect the temperature differences in the stock, so to say. So if there's not a lot of difference between the surface and the core, or the surface and the colder end of the of the slab. So that is the so-called lumped thermal capacity analysis. So you say this is just, you know, some piece of a body, so to say, which is at equal temperature, more or less. No? It can be different when you have a thick body. You know, you have a very high temperature difference probably between surface and the inside, the center of a slab, or the coldest end of the slab. So they can be very, very different. No? Cold, thin and thick, so to say. And to select S, you have to look at the situation. Do you have one-sided heating only, like it is shown here on the top? So you have an adiabatic line here at the hearth, or you have two-sided heating. Then you have the adiabatic line basically at the center of the slab. So there's no heat transferred over this line. It comes from both ends and meets in the middle, so to say. So then this is why you have to select S correctly when you look at the BO number. So one-sided heating is a walking hearth furnace on the left side. So you have a ceramic hearth sitting here with a walking beam system, heating only from the top here, as opposed to a double-sided heating, like in a walking beam furnace, where you have the option to fire from the top and also from the bottom, so to say. So this is depending on so one-sided or double-sided heating. That's the message. No? So look at a very brief example. So look at steel versus aluminium. When you say thermal thin requires a BO number of less than 0.1, you ask the question, is a steel slab of 120 mil thickness, 0.12 meter thickness, is it thin or is it thick at certain heat transfer conditions? We say here heat transfer condition is 40 watts per square meter in Kelvin. And then we say BO number is H divided by K times S is 0.1. Okay, this is still in the upper end of being thin, so to say. So it is still thin. And what does it mean for aluminium? No? We have a different heat conductivity, so 200 compared with 50 of our steel slab. So we have 40 again. This is the heat transfer divided by 200 here. And S, this is what we look for, should be less than 0.1, because this is the magic number for the BO thick and thin difference. So we say, okay, S can be less than 0.5 meters for an aluminium slab, and it still qualifies as thin. So it might be half a meter thick as compared with steel, which is only 120 mil thick. It still has no significant temperature differences in the slab. When we look at this BO number, we talk now about this heat conductivity, which is shown here. What is the heat conductivity of steel? The thermal conductivity of steel. You can see normal carbon steel. It comes down from the area of 50 watts per meter in Kelvin and goes down to say around 28 or so in the area of 800 degrees. So it's around the Curie temperature of 770 degrees. And stainless steel or some austenitic stainless steel types, they come from the complete other end. So they start at 15 watt per meter Kelvin, and they also go to this area of 28 in the area of 800 degrees or so. And then they are going up to the final heating temperature at 1200 degrees, and very, very much the same, so to say. So there's a huge difference in the BO number when you look at the area below 800 degrees. So this stainless steel is already thick material, so it has significant temperature differences in the stock in comparison with a carbon steel, for example, in certain heating conditions. So you cannot say steel is equal to steel. You really have to look at the type of steel and at the heat conductivity when you look at the heating process. So this is why that can be a completely different heating strategy for stainless steel in that lower temperature area here, up until 800 degrees. Look at the Fourier number. That describes, we talked about Biot before, this is the thickness, and now we talk about the heating time. And the Fourier number gives us the dimensionless heating time, so to say. What does that mean? So you have now we look just at the inside of the body, so to say. We don't look at the outside, so no external heat transfer anymore. So we say the conducted heat in the body is this expression here, so the thermal conductivity divided by S, the thickness, divided by the temperature difference from the surface to the core, times the time we are heating. And you compare this conducted heat with the stored heat in the body, so to say. So this is the equation. So we say energy conducted is equal or is approximately equivalent to the energy stored, which is basically this delta T. This is the temperature difference, because when you heat it from the outside, the temperature will increase, so a delta T. And that is related to the heat capacity and the density, and also S again, the volume of the body in the end. So in the end, when you have this equation, you take the S from here, from the right side, put it over to the left side. So you end up with S square here. So you have K divided by rho capacity, heat capacity times S squared times T. And this is the Fourier number. So that describes the dimensionless time. So this is alpha, the thermal diffusivity, times the time divided by S squared. And that is useful because, for example, for a plate, you can say everything Fourier more than 0.5 means that you have a completely developed temperature profile. So even the center of the slab is already affected by the temperature which you are, or by the energy which you are conducting through the slab by heat transfer, so to say. Everything Fourier less than 0.25 will mean you have some skin effect still. So the center of the slab is not affected by the temperature at all at the beginning of a heating process, for example, or if you have a very thick stock. No? So this tells us a lot, this Fourier number. So in the end, you can look at this in a simplified model. So you say you have a furnace at the temperature T infinite, and you have a stock which is heating up like this. So you have an initial temperature, and you have an end temperature of the stock after the heating process, and you have a temperature difference initially, T furnace minus the T initial of the stock, and you end up with a difference here in the end, temperature of the furnace minus end temperature. And so in the end, and this is what we will see now, is you will end up with this equation for a thin stock. So the temperature difference at the end divided by the temperature difference at the beginning is equal to E by the power of minus the thickness and the heating time. And that's very easy to calculate. We don't go into too much detail because it's a bit awkward probably, but this is how it works. You say, when you heat a plate at thin thickness, that means you have no significant temperature differences in the stock. You say the supplied energy from the outside to this body is equal to the stored energy in this body. And then you go through this whole calculation, including an integration. You will end up with this logarithm here. And you can calculate the heating time. And you can also, you see again this expression here for the temperatures. And you can calculate the final temperature of the stock after a heating time T, which is shown in here. We don't go into too much detail because that would cost too much time probably. So this is for convective conditions. So the supplied energy from outside is a convective expression. So H times a temperature difference here, a linear temperature difference. So this is very much different at a radiation heat transfer, because you are talking about T by the power of 4 when you talk about radiation. And so you have a slightly different expression and this awkward expression for the heating time in the end. So when you look at this expression here, which we found in this calculation, so here, when you look at this, when you modify this exponent here, so you modify it, so you extend it with K because there's no K, no heat conductivity in there. So you say you add a K here, you add a K here, then you end up exactly with these expressions for the Biot and the Fourier number. That's the message. So again, you will find this expression here. The dimensionless temperature difference is E by the power of minus Biot times Fourier. And that can also be generalized. And you can say the temperature difference, the end temperature, you can calculate from here, for example. Using this expression, you have n plus 1 factor here. N is 0 for the plate, 1 for the cylinder, and 2 for the sphere, because you have different volume to heated area relationships. So it's as I said, we don't go into too much more detail. So that's all good for thin stock, lumped thermal capacity analysis, Biot number less than 0.1. What happens if you have thick stock? There's a correction factor, so then you have a correction factor tau, which you can also use. This is shown in this diagram. That means a very thick body has significant temperature differences in the stock, so you have to use this temperature this correction factor, because in the end the temperature will be less. The end temperature will be less when you have a very thick body. An easier solution for convective conditions is to use these Heisler charts. They show you the surface temperature and also the center temperature of a slab. When you look at the Biot number, which is shown here on the horizontal axis, so Biot number, and the Fourier number, which is shown here basically in the different curves here. And you can also see at Biot number 0.1, this is the magic number between thin and thick, the center temperature will start to be affected with higher Fourier numbers, so to say. So here you have no change in the temperature at this point in the center, and it will only start to grow when you increase the time of the heating process. So I think we speed up a little bit, otherwise we won't finish. So what you can see here is topic gas and wall radiation. So obviously we have the Stefan Boltzmann law, which says a body inside another body in a heating condition is heated by the walls, by the surface temperatures. And you see here the range of the wall radiation between 1250 degrees C and, for example, 1000 degrees. So we end up at around 100, 130, 150, 200 kilowatt per square meter. But there's another component. This is the gas body itself in the furnace, because there is also radiation component of the gas. And when we look at the wavelength spectrum of the temperatures which we are talking in the furnace, so we are approximately operating here between room temperature and say 1500 degrees approximately. So we are in the infrared spectrum of the wavelength, so to say. And this is important to note when we look at the gas radiation, especially. So this is infrared in comparison to the visible radiation, which is a bit lower. It's smaller spectrum, wavelength spectrum. So to cut a long story short, we have all three atomic gases. They are absorbing and emitting radiation heat or energy. And they are sort of not like a gray body or a black body, completely continuously radiating over the wavelength spectrum like it is shown here, but gases are selective radiators, so they have just certain spectrum of wavelength where they radiate and others where they are sort of invisible, no? So they have no impact. No? In the end, you have a net gas radiation from a gas body to a wall by sort of expressing it like similar to a wall radiation. And so you have the emitted heat of the gas body here shown on the left side of the equation, and the absorbed energy on the other end, which is basically related to the wall temperature. So all these gases like H2O, so water, CO2, also CH4 and others, they are emitting and radiating in different gas spectrum. We have again an awkward chart here. I don't go into too much detail, but it's important to understand that the radiation of a gas is proportional to the content of the specific gas in the gas body. For example, 9% CO2 and 19% H2O, which is a typical natural gas combustion gas. And this you have to multiply with the thickness of the gas body. So P times L is the significant number here. So for example, at 1 meter thickness, 9% CO2 content, you're ending up here at 0.09. And same with water here. So that doesn't sound a lot, but you are multiplying this with the temperature in Kelvin by the power of 4. So this is in the end a significant number. What does it mean in the end? That's the question. If you sort of changing the gas, for example, from methane or natural gas to hydrogen or ammonia or methanol, so you can ask this question. Just a brief overview. So you have the heating content, lower heating value of these different gases here. And also the oxygen and air requirements to combust it stoichiometrically, and also the flue gas composition when you have air oxygen combustion and just air combustion in the end. And the chart here shows when you compare, for example, hydrogen combustion or ammonia combustion with natural gas combustion, you need 3 times more hydrogen volume to carry the same energy in comparison to natural gas, but you don't have a lot of difference in the air, and also not a lot of difference in the off-gas volume, in the flue gas volume. The same applies for ammonia also. So you wouldn't have to change a lot in the off-gas system probably, but certainly in the inlet system of the fuel for the furnace. In the end, when you burn natural gas, you have CO2 and H2O, so both components in the combustion gas. If you burn hydrogen, you have only water steam. You have no CO2. No? The same applies for ammonia. That leads to sort of higher temperatures. Here, there's a picture shown here with hydrogen content in the natural gas. So you end up with higher temperatures in the hydrogen fired burner because the adiabatic heat combustion temperature of hydrogen is higher. And this is what you see here. So you see here natural gas, you have 9% CO2, 19% H2O. With hydrogen, you have no CO2, but 30% water. And you can even have 100% water if you have just air as a combustion medium. You see the temperature of the hydrogen is much higher, the flame temperature, in comparison to natural gas. So there's a change, obviously. No? Just looking at this picture here, hydrogen flame, you almost cannot see it. It's almost invisible in comparison with a natural gas flame. What does that mean? The component of the gas radiations in a specific situation, here shown at 1300 degrees furnace temperature or gas temperature, radiating to a wall of 1100 degrees Celsius, gives you, with natural gas, you have a gas radiation of 70 approximately kilowatt hours per square meter, and with hydrogen only 26 because the CO2 is missing. So when you add this with to the wall radiation, you see wall radiation in this specific situation would be around 90. You have gas radiation much higher with natural gas in comparison to hydrogen. So you lose approximately 25% of the total radiation in this specific situation. So you have to really look at the different zones of the furnace and the layout of the furnace to determine what's happening in there. But obviously, just using hydrogen is not a solution. You have to compensate the lower heat transfer by, for example, oxy-fuel or wall emissivity increasing by ferrochrome coatings and all sorts of things. So it's not so easy as it looks like. It's not good enough just to look at the heating value. This is the message. So combustion gas composition, CO2, H2O, not flame temperature alone controls radiant heat transfer. That's the message. And now we talk about something completely different. This is an aluminum convection furnace to show there's no radiation at all. It's just convection. We are talking about low temperatures in the 600 degree range, and also very high, very low emissivities and absorption rates, because it's a very blank, very mirror-like surface. So completely different concept. Electrification, resistance heating. So this is showing typical radiation tubes operated with electricity. There are different options available to wire elements for resistance heating of furnaces. So it is possible to heat furnaces with this. I built furnaces in Norway 20 years back already, just heated by electricity, but just, I would say, normalizing furnaces in the area of 1000 degrees approximately. The main message here is shown here, a diagram of Cantal, that at the higher temperature range, say 1200 degrees or so Celsius, you end up with 25 kilowatt hours per square meter. This is the wall radiation. So the average radiation when you have a wall equipped with heating elements, so to say. So there's a limitation, obviously. So that's probably good for lower temperature furnaces, but in the higher temperature range, you have to be careful. You really have to look what you're doing. There's other operational questions, obviously, also furnace atmosphere corrosion, temperature fluctuations. You really have to look at what's happening there, and because in the end, not everything that's technically possible is useful in an operational condition, probably. So you really have to look at it in more detail. But it's possible. So electrifying the heating process is possible. We have a very high thermal efficiency of more than 90 degrees. When you compare it with fuel-fired furnaces, this is very high. There's no direct emissions, very, very good to control, so to say. Of course, you have to be careful with hotspots and other things, but it all can be managed. So at high temperature, high performance combustion furnaces, I think you really have to look at in more detail what you are doing there. As I said, you probably need a larger furnace geometry and longer residence heating times for the electrification case. So usually you cannot just say we don't use any gas, we just take some heating elements and stick them into the same furnace. You have to change the geometry of the furnace. Another topic is induction heating. very, very good concept. So the effective heat is an order of magnitude or above the fuel-fired furnaces. So why don't we use that for everything? Basically, is the question. Huh? So there are also some restrictions. And I explain the principles here. So it's very, very quick, very, very intensive, because the heat is generated within the body. You know, there's no external heat transfer. So when you have an electric current, an alternating current in a water-cooled copper coil, so to say, which is shown here, you put in a metallic body. The changing current in the coil is inducing also a current in the piece, in the body, so to say, in the steel body. So that's generating heat in the end. So this power is the resistance of the material times the current, which is induced by the power of square, and the heat is the power times the heating time. How does it work? There's a so-called penetration depth. This is the depth where the current is sort of developing in the body. You know, this zero in the center of the body. But it's 100% on the outside, and the value where it is only 37%, it is the so-called penetration depth delta of this specific situation. And that frequency which you are using, the frequency of the coil, so to say, of the current, has to fit exactly the diameter of the workpiece to have an optimum heating. You see there are different pieces. That's very bad, the red one. This is optimum, the yellow one. The other ones are also in the middle. So because we have the current here, the power is current times so square. So 86% of the heat will be generated within the penetration depth. This is the message here. So the penetration depth you can calculate. It is proportional with the resistance, electric resistance of the material. Steel is good. Copper has a very low resistance, so that would be very thin penetration depth. And very important, it is indirect proportional to the frequency. So 1 divided by frequency. And also the permeability of the material. So what does that mean? You have different penetration depths data. For example, you can have 10 millimeters in certain conditions, you know, at certain frequencies, and so on and so on. It's also very significant to note that steel, as long as it is magnetic, it is somewhere here in that area. So steel at 20 degrees with a permeability of 100 is reacting completely different in comparison to a non-magnetic steel or a steel in the area of above the Curie temperature, which is more than 770 degrees. So then it turns into 1, no? So from 100 to 1. So the heating is completely different in the high temperature range. What does that mean? For example, 1 kilohertz frequency gives you a very, very high heating time in comparison to 10 kilohertz. So it's very quick. It's quicker at 1 kilohertz because the penetration depth is a little bit higher. So you see in 10 minutes time, you can completely through heat a billet of 100 millimeter diameter. And that's very, very quick. So through heating 0.1 minute per millimeter, you recall the 1 minute per millimeter in a fuel-fired furnace. So it's really, really quick. You should not believe that the penetration depth and this inductive heating mechanism helps you with thick stock, because in the end, you will have a steel heat conduction, thermal conduction in the middle of the piece. So you have to wait until you have an equalization process as well for thick stock. No? So that's not as easy as it looks like probably. So you see here strip heating from 800 to 1100 degrees, very quick. In 15 seconds, you can heat a 12 millimeter strip from 800 to 1100 degrees. 15 seconds. It's not a lot, no? This is a forge heater. You heat in 8 minutes. You heat 100 square mil billet in 8 minutes from room temperature to 1200 degrees, ready for forging in 8 heat inductors, in 8 induction coils. This is how it looks like. One inductor after the other, water cooled. This is inline inductive thin slab heating in a steel plant. So you are casting steel strip, going into a furnace, going into the rolling mill, rough mill, next furnace, and the final mill in the end, and the down coiler here. So you can use intermediate heating here, depending on the temperature you need before rolling, for example. So you are basically going with the slab through this slot here, and you are heating up the slab in seconds. You know, it's very, very quick. So these inductors are very powerful. You can have up to 5 megawatt per inductor. Very, very useful. And this is certainly going into more use. You know, these inline processes. Very, very, very good stuff. So you can see this situation here in a inline heating rolling plant. This is how it looks like. You see here the inductors, one after the other, heating up in seconds. What you need. So heat quench and temper lines for tubes, a very interesting concept. So you start with a cold tube, for example, for drilling tubes or something like that, oil field tubes, go into induction coils, heat it up to 1000 degrees approximately, go into a quench with water, come back again, go into the tempering furnaces for the tempering, and also with induction coils, come out here on the cooling table, and that's the end. Very, very good concept, very small footprint, but you have to be careful because API standards, they also allow some eccentricity of the tubes. So you might have some material thickness which is different from one side to the other side, and that has an impact on the heating because the temperature will be much higher in the smaller area, in the thinner area, so to say. So you have to be careful when you do that. No? And the other concept is a hybrid heating of billets concept before rolling. So you have the furnace, you come in with the cold billet, go through it, you end the furnace not at 1200 degrees, you end at 800, 900, 1000 degrees, go into induction coils and heat up to the final rolling temperature of 1150 degrees, for example. That gives you the option to minimize the exposure time at high temperatures. So you minimize scaling and you have a very, very small footprint. You can operate the furnace at lower temperature and also optimize the energy consumption of the furnaces. So that's also a good solution here shown for a square billet, 160 mil square. In the end, you also lose some energy. You know, electric heating also in the inductive case, you also have some cooling water because you have to cool the water, water cool the copper coils. So you lose a lot of energy for the cooling water. So you shouldn't forget that. You know? So there's also some losses. So question is natural gas, hydrogen, or electricity? What is better? Certainly for heating purposes, the direct electrification is something you would look at in comparison to hydrogen if you don't have to, so to say, because you need a lot of electricity to produce hydrogen. I don't go into too much detail here in this calculation. So in the end, you will certainly use hydrogen in applications where it is of more use. For example, we are now, so thyssenkrupp nucera is building 740 megawatt electrolyzers for Stegra in Sweden. This is the green steel plant, which is built up in the northern part of Sweden. 740 megawatt electrolyzers to produce 2.1 million tons per year of DRI. For that, you use hydrogen instead of natural gas or coal. No? And for that reason, it's certainly a much better application for hydrogen in comparison to a heating purpose. No? To be honest. No? And here you see the electrolyzers we are building now. So the plant is almost finished now. The completion is it's ongoing. We are building this. This is a 20 megawatt unit here, only 20 megawatt. So it's huge. No? So it's 40 meters long and very, very powerful. So the conclusion is, wrapping up, consider your current heating strategy of the existing furnace to reduce the energy and emissions. Should make a health check of the furnace, including, very important, the air and the pressure of the furnace. Heating with alternative fuels is possible. Electrification is technically possible, yes, but also consider hybrid solutions because there's not one fits all solution. And also check the impact on the final product because everything has an impact on the steel you're heating. There is no free lunch, so all options come with energy losses and also operational challenges. No? So cost and so on and so on. The future belongs to heat integrated solutions, is my opinion. So minimizing reheating requirements. So the best thing is not to have the need for reheating. Why are you cooling down to room temperature, for example? Why don't you use a higher temperature? If it is possible, you should do it. And this is the way it goes with these inline solutions, which I have shown before. And overall, let's never forget that we are in a very, very competitive industry. So 1 kilo steel costs less than a liter of mineral water. It is a very competitive industry. So what we do has to make sense. It has to be operational sensible. It has to work. And we have to look at the cost of what we are doing. And with this, I want to thank you very much for your attention. You can always reach out to me if you like with questions or anything. And yeah, thank you very much for your attention.
Thank you, Johann. That was absolutely fantastic. Great presentation. Thank you for putting that together, taking the time to put that together for everybody. I found it fascinating, very relevant for the steel industry, everybody in this webinar. So I'd like to take some questions from the participants.
Yep.
Okay, I think there is a question from Christopher Liburn. How can we access this recording? What we can do is we can send, I know it will be recorded in the AIST website, but if you could shoot an email, I can send the link to you to watch it later. And Michael, do you want me to ask a few questions or everyone else thinking for a new question? So that was a really good presentation, Johann. It was really informative, and I myself learned a lot. So and you covered the detailed part of the industrial aspect of it, but you also got into the theoretical part of it, which is covering the both world, I will say. So that was quite interesting. I'm just curious about what do you think about where you see the strongest lever for reducing energy consumption and emissions in reheating? Because at this point, we are thinking about reducing emissions in different part of the steelmaking process. So where do you think that we could use that lever to reduce energy consumption?
Thank you, Saba, for your question. So in the end, as I said, there's no one fits all solution. Generally, I think reducing energy and emissions requires to have a close look at the existing furnace structures and the heating strategy, as I said, off-gas temperature, preheating temperatures of air, etc. This is what I mean with a health check of the existing system. You obviously can sort of play around with all the parameters, like off-gas temperature, as I have explained it. You certainly would look at sort of more integrated solutions, if possible. I always say if possible, because we don't live in an ideal world. So if possible, you would avoid reheating as far as possible. You certainly would look into hybrid solutions, like partly electrifying a process. When you look at the emission part, for example, you have a very high efficiency electric heating, for example, in certain parts of the heating process. Otherwise, you can probably not electrify. But in the end, it's also depending on the economies. No? When you look at the real world situation, you really have to look at the cost of electricity, the cost of natural gas, the cost of hydrogen, and so on.
I'm just curious about the induction heating. So do you see a pickup on that, like as we are looking into more electrification and such? Do you think that technology is taking the induction path a bit more? Like what sort of thing happening in the market? Do you have any idea? Can you give us an idea?
Yeah, generally, it's certainly, I think it will pick up more, especially also in areas when you look at the European Union with the CBAM coming up, so this carbon border adjustment mechanism, and also the carbon pricing, which is happening there. So the players there, they have to look at reducing their emissions somehow. Yeah. So they will use each and every opportunity as long as it is economical. No? So it's a function of the CO2 price, it's a function of electricity prices and gas prices in the end.
Yeah, and I have seen you mentioning about the using hydrogen. So do you have an idea what price that hydrogen could be, like economically viable solution if you're trying to use it in reheating furnace?
As I said, using hydrogen for a reheating purpose is probably not a perfect solution, I would say, because you lose a lot of energy during the production process, at least when you talk about green hydrogen, because you have electricity on the one end, and when you end up in the furnace, you lose approximately, I would say, 75% of the energy already by all these conversions. So looking at that, you certainly would prefer to go into electrifying processes first. When does it become economical? So that's also depending on the CO2 price, which you have to sort of respect in the calculation. But usually for direct reduction purposes, we talk about, say, $2 to $3.5 US per kilo hydrogen. That would be
that's probably the ideal price. We have a question from Benjamin Roberts asking about what are the typical internal pressure operating points you see on reheating furnaces. He's asking about internal pressure, and then there's additional question, and where are the internal pressures typically measured within the furnaces?
A very good question. Thank you for that. So usually you have to measure the pressure at the height of the stock approximately. So not at the top of the furnace and not at the bottom somewhere. So you really have to look at the level of the stock, so to say, because this is what is interesting us. What is the interesting part? How much air is coming into close to the surface of the steel? No? That's the question. And the pressure would be, I would say, a slight overpressure of maybe 1 millimeter water column or something like that, 0.1 millibar or something like this. Just a little bit more than outside. I mean, this is a very rough indication, but it should not be much more, because then you're blowing out the combustion gases and you lose energy that way.
Yeah, so thank you, Benjamin, for your question. And I was really amazed about the amount of loss we are looking at. Like when you talk about the losses from this furnace, it's quite a lot.
Yeah.
And what sort of I know you have discussed few of the things before, but just wanted to highlight what sort of I think measures can be taken to minimize those losses from these furnaces.
Really look at the flue gas temperature, number one.
Yeah.
How can you reduce it? Probably not, but you can use the heat to preheat the air. So you can look at the regenerative burners, for example, in the high temperature area. Of course, regenerative burners are not easy to handle because there's a lot of mechanics involved and so on and so on and so on. But in the end, you should look at some way finding a suitable solution in the suitable sounds of a furnace for air preheating. I think this is the key. Obviously you can try to reduce the flue gas temperature. The question is how. No?
Yeah, sure. Michael, do you have any thoughts or questions?
I thought the point that you made about product quality, Johann, and the importance of monitoring product quality as the changes are made to the furnace and the transition to electricity or using different fuels. Is something there that you can comment on your observations?
I mean, for example, in a natural gas-fired furnace, some people try in the high temperature zone. They try to operate with a reducing atmosphere. That means you have less oxygen than you need for combustion. That does help, so to say, a little bit. So you have less oxidation a little bit, but this is not a good solution because you get a sticking scale. The scale is not oxidizing enough, so it does not remove itself from the surface of the steel. So that is not a good solution in the end, even if you have less scale probably. When it is sticking on the surface, you would roll it in and you have some troubles then afterwards. No? So you better operate at stoichiometric conditions in the atmosphere and do it like this. When you have electric furnaces, I mean, you obviously have air in the furnace, so you also need some, or do you have just radiation? So you need probably some convection, you need some overpressure, no? So a little bit of overpressure, you need some ventilation system or something like that. No? So you really have to look at the specific situation, I think.
Thank you. Do we have any other questions on the Q&A?
Okay, so there is a question from Dr. Ramadas Narayan. He said, could you please share some thoughts on optimizing the thickness of the furnace wall?
Yeah, I mean, the thickness of the furnace wall, they are usually in the range of 400 millimeters, 450 millimeters, including kind of safety lining or outside thermal insulation and an inside hot working insulation or refractory. So it certainly, when you look at a furnace with temperature changes like batch type furnaces or so, you would use a fiber lining, so a very light lining with low thermal capacity, so you don't have to heat up the wall all the time. When you look at a continuously operating furnace, you can have a brick or also a concrete lining because you don't change the temperature of the lining so much. No? So at a batch type furnace, you have to go for fiber linings. No? It's all possible. So all at these temperatures, it can all be done.
I think Michael got disconnected or something. Just to move on, I was curious about the scaling issue. So can you give us a bit of idea how much, when we're talking about scaling, how much we are talking about that?
Scaling, usually in this type of furnaces, you have 0.8%, 1%, 1.2% in a continuously operated furnace at these temperatures of 1200 degrees or so. So this is certainly a good value, at least when you are in the 0.8% range. As I said, it's a function of the surface area of the steel you are heating. it can be 3% in a rotary hearth furnace. Scaling starts at 550 degrees approximately, because then oxygen and iron are combining with each other. Excessively, it is more than 800 degrees. So what you should do is minimize the exposure at high temperatures, if possible. So for that reason, induction heating is a very good solution, for example.
Yeah. So there is a follow-up question from Ramadas Narayan. Thanks, fiber lining and concrete lining. Thanks. Will have some impact on the type of fuel used.
Sorry, can you please repeat?
So Ramadas Narayan, who asked about the optimizing the thickness of the furnace wall, which you have replied that use fiber lining or concrete lining. He was asking, will have some impact on the type of fuel used? Does it matter? Like what sort of fuel you're using?
Yeah, I mean, usually there's a discussion. So there's a discussion now. What does, for example, hydrogen firing mean for the refractory of furnaces in general? No? You also see this in direct reduction furnaces, because hydrogen. When you look at the water steam only, so H2O, that it's not 100% known what the impact is. So there's not a lot of experience. And when you certainly have to be careful when you look at the colder parts of the structure where you have condensation potential. But usually at these high temperatures, at this type of furnaces at least, that should not be a big issue, I think.
Yeah, so there's a scope of innovation and more learning on this, I guess. So Christopher Baron has added question, what changes has machine learning facilitated, and are there any technologies that you are excited about?
So I'm certainly excited about induction technology, because it offers rapid heating, it offers internal heat generation. It is certainly complicated in a way, because when you look at the rough environment of a rolling mill or a steel plant, this is a very nitty-gritty solution, so to say. But in the end, you can industrialize it, and this is done in practice. No? So certainly very fascinated also.
Yeah, so we have a PhD student, Tarindu, who is doing his PhD on induction furnaces, induction reheating furnaces. So he has been doing lots of work, and the work has been published. So that's just to keep an eye on that. So there's another question from Dinakar Sagapram. I hope I pronounce it correctly. Are there any literature studies quantifying the energy consumption and carbon emission associated with reheating furnaces?
I think when you look in the literature, there's lots of studies available since many years. So yes, the answer is yes.
Okay. And Benjamin Roberts added, have you seen benefits of precast refractory solutions in reheat furnaces in terms of better efficiency and reduced drying out times as opposed to refractory cast in situ?
Yeah, definitely the precast elements, they offer much quicker installation times, much easier to handle during this phase. In the end, in the operation, it doesn't really make a huge difference, but certainly during reconstruction and repairing furnaces, definitely.
Okay, and how are the precast refractory they are made of? Like what material usually?
Yeah, they are usually made from concrete, so you have a low cement refractory basically, and that's tempered before going into the furnace, so you already get rid of the crystal water and the physical water, so it's ready to be installed.
Yeah. Okay. Michael?
Yeah,
often alumina, I think, is for cast materials.
Alumina, high alumina usually, low silica usually. It's depending on the temperature zone of the furnace. So usually you have more than 45% at least alumina or malite structures there. Yeah.
I had a question, Johann, around, you mentioned wall coatings. Do you see wall coatings being used in furnaces? I think you might have meant around the internally reflective coatings.
Yeah, it's not really reflective. No? So I mean, I personally, my opinion is it is not a durable solution. No? Let's put it that way. No? This is my opinion. No? I have not seen it used a lot, to be honest. The impact is not to reflect so much. It is the sort of you increase the emission factor. That means it gets more black, so to say. You know? So from lighter gray to more black. That means the heat, the temperature of the surface of the refractory, together with this higher emission factor, radiates a lot of more heat, or a little bit more heat. No? That's the mechanism. No?
Yep. No, thank you.
And there is one question, Michael, I just wanted to add. What, if any, are the anticipated or measurable effects of increasing furnace wall emissivity in fuel-fired furnaces?
No, you certainly, you have seen it probably in the calculation when you have this radiation heat exchange between two walls. You know, you have the Stefan Boltzmann law with d by the power of 4, and also an expression with which describes the geometry of these two surfaces, you know, the steel surface and also the wall surface, and that includes also the emission factors, the emission coefficients of both walls. So the higher the emissivity, the better the heat transfer. So that, for example, leads in copper furnaces, you know, where you have a very blank furnace. When you make copper foil, or so, you have a reheating furnace, because the copper is like a mirror. They are coating it with a kind of green color just to increase the emission factor of the surface to make it more acceptable for radiation. No? Otherwise, it would be reflected completely.
Thank you, Johann. So I think for the audience's sake, I have put, so there is AIST symposium coming next week. And if you're interested, I suggest you register. I put it in the comments so that everyone can see it. And there is also online option. So for example, you cannot travel, but you'd like to join, so you can join virtually. And we also have a DRI courses coming soon. That will be in-person courses, and it is with coupled with Hill CRC, and so you can also do that courses. And Professor Jeff Brooks and Johann here will be doing the course jointly. And yeah, so if you have any questions or anything, we are happy to help you and help you to get the best of this AIST membership.
Thank you, Saba. The DRI course is on the one next week is on the 10th to the 12th of February, and the DRI course is on the 9th to 10th of March. And as I mentioned at the start, or the calendar schedule for all the AIST courses are available on the website, the calendar button at the top of the website. So if there are no more questions, I'd just like to thank you to everyone for your attendance. Thank you especially to Johann for preparing and presenting this training webinar. I think everyone would agree it was absolutely fantastic, very informative and appreciated. Thank you to AIST for hosting the online seminar for the Australian and New Zealand chapter. AIST is an excellent organisation and just unbelievably valuable for the international steel industry. If there are no more queries, I will now close the webinar and bid everyone a good day.
Thank you so much.
Thank you both, Saba and Michael.
Thank you. Thank you, Johann.
Bye, everyone.
Goodbye, everyone, and thank you.
Thanks.